keep that in mind. Okay. So what were we talking about last time? Yeah. So we were trying to separate out the Schrodinger equation and show that it was separable. We shortened our wave function. Instead of writing everything out with M, L, L, and so on, how did we shorten our wave function? Into what two contributions? Yep, R, and what was the other one? Y. So what was R for? Yep, it's the radial function, and what was Y? Yep, theta and phi it depended on. It was the spherical harmonics, the angular part of the wave function. And we got down to a point where we had separated everything out. And we didn't have it written in this format, but I'm going to write it this way. 2, that's a 2 out of the second derivative. So I don't know what that was, but I thought it like, I work way too much on a computer because I almost stepped back and was like, what did I press wrong? Like, here we go. Oh, I know. And especially as the weather gets warmer, it's harder to focus. And then I open up the windows, that's even worse. Okay, what else do we need in here? Yep, we're gonna worry about the Y stuff at the end. We write it. Oops, this should be a negative. Whoa, what am I doing here? I want to get rid of that thing. What do I need for the Y portion? H bar squared over 2m, and then what else? Yep. 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 And that's all equal to what after we divided everything through? Yep. Okay. And then, even though this is big, long, looks ugly, we could divide this up into 2 portions. What does this portion depend on? Yep, just R. Right, it should be a mu. So this is all on R. Oops, need to extend this. That's all R. And then this thing is theta. And what else? Yep, phi. And then we said, hey, we've already tackled this guy, right? It's all made up of L's, and we got to the result of h bar squared, L plus 1, all over 2, like that, right? He agrees with me. Is that as far as we got? Okay. So now, if we take this and we plug it in here, we're going to get a new result. We'll show what we'll do in a second to get past this too. So plug that guy into here. And what we get as a result is all of this stuff written out yet again. I'm just going to do it along here. R squared over R. R plus squared B I think we actually left something out. I think we, let's look back. And that's all equal to ER squared. Okay, we know what this Z is. We'll deal with that in a minute. But again, we arrive, what would you do now if you wanted to make this a differential equation that's easy to solve? Yep, this is a constant, so you can move it to the other side. What are you setting this side equal to? 0. You're going to set it equal to 0. Okay, there's a known set of solutions for these guys that follow that sort of format. So the known solution to this differential equation is associated I'm going to butcher this guy's name. How would you say that? That's how I would say it. Like you're I probably have to go talk to Dr. Aminoff to actually know how to for real say that, if that's French or is it Italian. I don't know. Looks French to me. With these polynomials. That are restricted by two numbers. And these two numbers must be whole numbers. What does, how would I be more formal in writing this guy out? What subscripts do I need here? Yep. Yep. And what does it depend on? Yep. Okay. And then R. What does R depend on? Yep, little r. And there's one more subscript that actually should go here. N. So now, what's going to dictate what the solution to this is, our wave functions? What two quantum numbers do we have to know? Yeah, we got to know N and L. If we know N and L, we can get all the other things in here. And there's one more restriction on the value of N and L. If you go back to your rules of quantum numbers, N can be any whole number, right? What is the rule for L? Yep. So therefore, what's the restriction on these two? They can't be equal to each other. What else about their magnitude? Yeah. So that's why there's this rule here when you're determining the quantum numbers. It actually is a restriction based upon the solution to that differential equation over here. For it to work out, your n value has to be less, or excuse me, your n value has to be greater than your L value. Otherwise, mathematically, you don't know the answer to this solution. Okay. From these restrictions, for what we're going to call the hydrogenic wave functions, the radial part where n has to be greater than L, and the angular part deals with which two quantum numbers? Yep. That also has to be true. And those sets of quantum numbers, rules that you learned in Gen Chem, they're all based off of this. Okay. And now you see kind of why in Gen Chem we just go, these are the rules, learn them, move on. Because how much time did it take to get to this point, / how many classes did you have to get through to even understand what the hell this meant? Yeah.
12 or 13 weeks?
Yeah. 12 or 13 weeks plus, you know, how many semesters of calculus and differential equations to get to that point. That's why when people are talking about quantum mechanics, most of the time, like they say, oh, if you understand quantum mechanics, you're a liar. You don't really understand quantum mechanics. That's not true. Most of the time, popular scientists say that sort of thing because they just don't, they can't conceivably explain what's going on to somebody who has no mathematical background. It's like describing what blue looks like to somebody who's been blind all their life. It's like, that's nearly impossible, right? So a lot of questions I get associated with this sort of stuff, I legitimately just say, you do not have the mathematical background for me to explain it to you. And I'm pretty sure in your class I said that like 4 or 5 times to people who had questions, and I know in your class I said that a lot, Lily. Yep. It's because I just can't talk to people about it.
You have to be a chem major.
Yeah, or like mathematicians and physicists, I can talk to them about that sort of stuff too. But yep, biochem too. Tessa could we could get her there. Yeah, it's a special club. All right, now I handed out a sheet to you guys, and if you notice, there's a list of a bunch of different functions on there. You'll see you have a radial part, and I think I have the angular momentum part that you've had in the past. So you need both of those things to build the hydrogenic wave functions. We're going to talk about that in a little bit and how to utilize it, but before we get there, let's talk a little bit about energies and about how all of this crazy stuff right now, it seems highly theoretical. We're going to find a convergence point between experiment and this pure, what we're going to call ab initio first principles theories. We're going to find something experimental that drops out of here that made people go, this is right. It's crushed it in every regards, and now we have another experimental thing that works. And hopefully that dude just sliding metal around outside stops. I'll get rid of that too. Disgusting biochem stuff.
He's like, yeah, you have to show this mechanism. He says a box this big. Like,
yep.
It's like a 14-step mechanism.
Yep, that's why I hated. Yeah. And like, how are you meant to just lock that all in? It's like the citric acid cycle, Krebs cycle. So when we're talking about the energies of this system, you can show that this is true. If you apply those hydrogenic wave functions to the Schrodinger equation, you're going to get this out as your energy. The kind of interesting aspect is what's the only quantum number that the energy really depends on? N. L and ML are still hidden in there, but what do you know? Like, for example, let's say I have an L is equal to 1. What are my possible values of M sub L? Yep. And if we draw an electron configuration diagram, what type of orbital are we talking about here with an L is equal to 1? Yep, and how many dashes should I draw? What do you know about the energies of these systems? Yep, they're degenerate. Really, the only spot that they relied on was that N value here. Okay. When we move up to more electrons, that's where we're going to have to start to think about L. But we'll get there in a bit. Okay, so what's that mu again? Yep, it's the reduced mass. In this case, it's the reduced mass of hydrogen, which is equal to 9.104 times 10 to the minus 31st kilograms. Okay, looking at this expression, what do you notice about all the values in here? What was that? Yeah, they're all constants, basically. The only thing that you can, what's the only thing, only two things really in here that you can change? Yeah, N and then the nuclear charge if you really wanted to mess with that. So, question, what happens we simplify these constants? If we consider the H atom, let's just look at this first part here. E to the fourth mu 32 pi squared E naught squared. Okay, let's write down the value of these constants and their units. Anybody remember what the charge of the electron is in coulombs? Yeah. Yep. Okay, mu, I gave you mu. Okay, then we just got 32 pi squared E naught. Anybody remember that one? Yep, it is 10 to the negative 12. Hey, you're better than me. I didn't even know 10 to the negative 12. Do you remember what units that thing had? Yes. Coulomb squared joules times meter. And then we got H bar 0.46 times 10 to the minus 34. What are the units on that guy? Or what are they for, yeah, times, yeah. Then we got to square that thing. Oh, we got to square this thing too. That to the 4th. Everything else is good. Okay. If you punch all of that junk in, what units are you going to get out in the end? Coulombs are gone. Mm-hmm. It's a joule. Okay. Now, if you look at it, you have to do some manipulation, but it ends up working out to be a joule. You get that as a value. Does anybody know what that is, or do you remember? Maybe from Gen Chem or way early on in this class. You guys know? It's related to that. If you don't, that's okay. This is the Rydberg constant. The Rydberg constant is when you were considering electronic transitions in the H atom, going from the ground, like from a ground state to an excited state, you had to look at the difference where it was. Yeah. Delta E R sub H 1 minus Ni squared minus 1 over Nf squared. Like that. So remember, yeah, that was really long ago, but we taught, like general chemistry, we talked about it, and at the beginning of the semester we did. This is empirically determined. So experimentally, they measured this. We have just calculated it completely from theoretical ideas. We show a connection there. We're right, and we know we're right. We're modeling this very well. It's crazy that you can find that, but can we find other constants too that we could say, yeah, this makes some sense? Okay. Let's talk about some other constants that we can see that fall out of this stuff. So when we look at the radial part, or coming up with the hydrogenic functions, there's another symbol on there that we probably didn't talk too much about, but when you look in the radial part, what do you notice is in there? So like, let's look, for example, yeah, rho. And what is rho? Yep, it's related to the electron density. What other things are in there? Yep. What's A? Yep. It's atomic radius. So rho, we're going to use to combine some stuff together. It's 2zr over NA. And then A is related to the mass of the electron over that. A naught. So now you might be asking, what's A naught? It's a collection of constants. This is known as the Bohr radius. When you used Bohr's model of the atom and you were calculating like the orbit or the distance that that electron was moving from the nucleus, this is the value you would get. Okay. There's ways to make this a little bit simpler and get around these things. So if we look in that denominator, what do we have in this denominator? It's a reduced mass, right? So we got 1 over mu, which is made up of what? What two masses? Yep. Yep. In this case, the nucleus is the mass of a proton, right? So then, if we look at this expression, A is equal to mass of electron over mu. You get mass of electron over mass of the electron plus nucleus. Let's try to simplify this. What's that going to get you? Yeah. Now, what's the value of this term going to be? Do the mass of the electron and the mass of the hydrogen equal one another? Or mass of the proton? Yeah. It's going to be really, really small. These two differ by a factor of 10 to the fourth. So what could we approximate this to be? Yeah. So therefore, in most of the cases we will see, do we have to plug in junk for this? What's it approximately equal to? Yep. It's approximately equal to the Bohr radius, at least for a hydrogen atom. So on that sheet where we have a bunch of different radial functions, like for example, R and L of R, let's say we're looking at 1, 0. What type of function is that? So with an N is equal to 1, L is equal to 0. What's the orbital type where L is equal to 0? Yep, S. N value is equal to 1. So what is this orbital? Yeah, it's a 1s. If you look on your sheet, you would see 2, Z, A, 3 halves, rho, over 2. However, if we ever want to work with that, we need everything in terms of R. What could you approximate that to be? We got 2 times z over what? Yep, a naught. 3/2 e to the negative. We want to plug in that stuff over there. 2z r n, what else? Yep, a naught divided by 2, like that. Let's simplify that further. Sorry, going too fast. So what things are going to cancel out in here? 2. Yep. Anything else that you could get rid of? Specifically, if we're talking about a hydrogen atom. Yeah. Z is +1 for H atom. So then, same with here, right? What does this become? E to the negative R, like that. For what things do we have to specify? Which type of atom are we talking about here with this radial function? A hydrogen. It's going to change if it's a lithium or a helium that has 1 electron, so keep that in mind. Do you feel comfortable with that and see how we got down to that point? It's going to make the mathematics a lot easier, getting rid of a bunch of these constants. The other thing is what's our n value here? So that's also going to go away. Use what's given to you to make it simpler. Now, we can use this to describe the H atom, its electron density distribution, and we can use a lot of other tricks to get around having to worry about that angular part. We really only have to focus on this bit. Okay. Well, let's ask another question of setting. So we only dealt with the radial part. Let's look at everything together. Mao, Katie, erase this side. Okay. That sheet that you have in front of you with all the different radial wave functions and angular functions, spherical harmonic functions, is provided to you on every Quizlet going forward in the final. So you do not have to write those down if you don't want to. So what does wave function of a 1s orbital look like? Okay, psi. What does psi depend on? Yep, r, theta, phi. We have shown what can you do with the wave function. What can you break it up into? Yep, r, which depends on what? Yep, little r. And then what else do we got? And what does y depend on? Yep, theta and phi. What other things do I need to indicate in here? Yep, N and L. With R, we indicate the N and the L value. What's our N value? 1, and our L value. How do you know? Yep, we're told a 1s orbital. So that tells you the N value, and then the orbital type tells you the L value. Okay, with the spherical harmonic functions, what do we have to indicate there as a subscript? Yep, we need L and M sub L. What's our L value? 0. What's the only possible value of M sub L we can have? 0. Okay. So now, we've already dealt with this R sub 1 comma 0, right? So we showed how to distill it down to simplistic or more simplistic values. Is it 3 halves? Okay. R, negative R, A naught. What about, so that's for R. What else do we need? Y. Tell me, look on your tables, what's your Y value? Like that, right? And that's just this part. Actually, probably should have used red. Okay. Do you feel like you can construct wave functions based upon this information? How are we doing on time? 109? Okay. Next, we're going to look at the probability, or finding an electron with a given probability in a 1s orbital utilizing this wave function. So, sample. What is the probability that an electron in the 1s orbital of a hydrogen atom will be within a radius 2.00 angstroms from the nucleus? Okay, what are we looking for? Probability. What information is important to us that we'll need? Yep, 1s orbital of, yep, because that'll change the way it looks a little bit. What else? Yep. Okay. How do you suggest we start? What's the general equation to figure out a probability? Yep. Yep. D tau. And what about my integration limits? Yeah, we generally put A to B just over some limit. Okay, now we got to change that up for our situation. How many integral signs do we need? How many? 3. First one, what do you want the first one to be for? R starts at what and goes to what? Yep, 0 to 2.00 angstroms. I'm going to make this bigger, sorry. So we're going to our radius of 2 angstroms. Next one, what do we got? Yep, theta goes from 0 to pi. Last one. Yep, and that's for what? Yep, for phi. Okay. Now, what do we got to do next? Figure out our wave function. I do something wrong here. Oh no, I didn't do anything wrong. Okay. No, maybe I did do something wrong. Let's look back. We could have simplified this further. 2 over square root of 4. There we go. That's our wave function. Okay, I got to take the complex conjugate of it. Is the complex conjugate going to change anything? Why not? Yep, there's no i's, so we got this. Square root, and remember, these are already normalized, so we don't have to worry about normalizing anything. Okay, what else do I need in here? And what else?
Oh, and the sign.
Sine of what one? Theta, yep, and one more thing. R squared. Then we can do dr, d theta, b. Okay, how do you want to tackle this thing? Yep, get the 1 over pi out of there. We can do that. Yep, we're going to get 1 over pi. This times this. What are we going to get out? Oh, those exponentials, it's been a while. A naught to the power of what? Yep, a naught to the power of 3. Okay. And then what else can we do? Can we separate things out? Yep, these e's are going to get smacked together. What else are we going to put with the e's? Yep, r squared, because they all depend on that. What about this term? It's left over. Yep, goes with that. That guy, just b. So we get integral. Let's do theta, 0 to pi, was it? What's going to go in this integral? Yep. D theta times integral. Which one do you want to do next? Okay. R from 0 to 2 angstroms. What do we got in there for our R function? R squared times what else? Negative. Yep. dr. And then finally, phi from 0 to 2 pi. Okay. That guy, what are we going to get? Yep. So we get 2 pi, where the pi's cancel. This guy. Integral of sine is what? Yeah, negative cosine. We just got to go from 0 to pi. The integral of that one is a little trickier. You can get it from a table. But what it ends up being is e to the negative 2r a naught negative a naught r squared over 2 r a naught squared over 2 r a naught to the third over 8. Evaluated from 0 to 2 angstroms. When you evaluate everything in the end, you get 0.981. What does that 0.981 mean? Yeah, 98% chance of finding it within that range. You don't if you keep angstroms here. So as long as your angstroms have the same units, or your A naught, you're in angstroms, you should be okay. Does that answer your question? Okay. There's a little cheaper, easier way we could have gotten around this too. These terms are normalized, so we could have split it into the radial parts, and we could have written it kind of like R star, Y star, R, Y with some integrals. And we know we're only changing the radial part. We're not changing the angular parts. What do you know about multiplying or taking these two together? So if I had this, what's that equal to?
1.
Yeah. Yeah. Because it's already normalized. So you could use that as a trick too. Okay. So we went through how to utilize that, what do the hydrogenic wave functions look like, and how to calculate some probabilities. What we're going to do next time is look at what's known as radial distribution functions, which give you an idea of the probability of finding an electron as you move away from that nucleus. And we'll talk about why there are some little blips there